we have a real sequence, and given that it's an iterative sequence, next term is equal to sine of previous term. And the first term, x naught, is in between 0 and half pi. And show that xn is asymptotically equivalent to square root of 3 over n. So meaning we want to show that limit as n approaches infinity of xn over square root of 3 over n is 1. This is what we want to show. And so first of all, we notice that sine, so in radius. So first thing we notice is that if we say this, so the radius is 1. Right? So sine of this degree is xn minus 1. Right? So sine xn minus 1 equals the length of this line segment. Because like I said, radius is 1. So that is sine value. So what is this value? xn minus 1, right? xn minus 1 is in fact the length of this arc, right? That's the definition of the angle in terms of radius, right? That's the arc length over the radius. The radius is 1. And so xn is only this length. So definitely xn is shorter than xn minus 1, right? So meaning the sequence is monotonically decreasing. Of course, it is bounded below. Right? Every term is positive. Right? So it has a limit. So that we can say for sure. The limit does exist. Right, denoted as x. So this time we can take the limit on both sides. X equal to sine x. And also it's in between 0 and half pi. So it only happens when x is equal to 0. Otherwise, it cannot be true, right? So we immediately conclude x is 0. Now, and we're not done, right? All we know is that limit is 0. But we want to show the limit is approaching 0 at the speed of square root of 3 over n, right? In other words, the sequence is approaching 0 in the order of square root of 1 over n, right? So it's approaching 0 very slowly. So in other words, all we have to show is that limit of n approaches infinity of x squared n over 3 over n is equal to 1, right? Is this true? In other words, is this true? So times n times n. N times x squared n. All right, then we multiply by 3 on both sides. Right? So is this limit equal to 3? Right? N times xn squared. Right? All we have to show is that n times xn squared. Right? So that is n over 1 over xn squared. Right? Using Stoll's theorem. Stoll's theorem tells us that as long as the denominator as a sequence is monotonically strictly increasing to infinity, right, then we can apply it. So xn is monotonically decreasing. So 1 over xn squared is monotonically strictly increasing to infinity, right? Because xn tending towards 0. That's why its reciprocal is tending towards positive infinity. So this time we can apply it. So we can take the difference of previous term, next term, previous term of n. So n plus 1 minus n, right? That's the bn plus 1 minus bn. and over whatever, an plus 1 minus an. So 1 over x squared n plus 1 minus 1 over x squared n. Right, as long as we can work out this limit, then we're done. So that is equal to 1 over x n plus 1 squared is equal to sine square xn minus 1 over x squared n. Right. So that is equal to xn squared sine square xn squared minus sine square xn. Right? Taylor expansion. Xn squared sine square xn squared minus xn minus 3 factorial xn cubed plus little o of xn to the fourth quantity to the power of 2. Right? I've just turned the sine into this, and then outside I have a square. So little o means a sequence approaching 0. Right? Some sequence doesn't have to be unique. So as we multiply out everything, so we can actually have sine square xn square. So we first, for example, we use this term multiplied by itself. Right? X squared. This term multiplied by this term. Right? So it's xn to the fourth over 6 negative. But I still have to use this term to multiply by this term, so I have twice of them. Right? So I have exactly negative x to the fourth and over 3. Right? Next, I just use this term multiplied by this term. So little o of x n to the fifth. Right? But still, I can categorize it into little o of x n to the power of fourth. Right? That's perfectly legal. And so this still multiplied by, for example, itself. Now I have x n to the sixth. I can still put that into little o of x n to the fourth. And so is this one. This one times this one, like little o of x n to the seventh. But still I can say it's little o of x to the fourth. And so eventually I still have plus little o of x to the fourth. And xn squared sine square xn is gone, plus xn to the fourth over 3 plus little o of x n to the fourth. So I want to show that the limit of xn over square root of 3 over n is equal to 1. Then I can show this. All I have to show is this. And that, which means all I have to show is this. So using Stoll's theorem, and also replace xn plus 1 with sine xn. Eventually, I have reached to this result using Taylor expansion, where little o means some sequence that's approaching 0, which means this whole term is approaching 0 faster than xn to the power of fourth. So now I just have to divide everything by xn to the fourth. Right? So eventually I have 1 over 3 plus little o of just 1. And on top I have xn squared over xn to the fourth sine square xn. Right? So this time xn to the power 2. So sine xn over xn, right, as xn approaches 0, like I said, previously, I've shown that xn actually approaches 0. Right? As I take limit on both sides, x equals sine x. Right? In this interval, x has no choice but to be 0. Right? Limit already exists. It's monotonically decreasing and also bounded below. So this time, little o of 1 means some sequence approaching 0 times 1. So this term is gone. Right? This term approaching 0. And also this term, like I said, sine xn over xn approaching 1. Right? So this whole term approaching 1. So the whole thing approaching 3. So this is exactly what I need. I've shown the limit of this is exactly 3. Right? The limit of this is exactly 1. Right? So really, meaning x is approaching 0 at the order of 1 over square root of n, or 3 over square root of n.